Hi, this video is on tangent lines and velocity problems. Let's dive right in. I'm going to pull up the PowerPoint. Okay, so we are now looking at the PowerPoint. Let me put this in presentation view. All right. All right, so the tangent line and velocity problems. This is our first section of the semester. Woo! Let's start off with the tangent problem. So the word tangent is derived from the Latin word tangens, which means touching. Thus, a tangent to a curve is a line that touches the curve. In other words, a tangent line should have the same direction as the curve at the point of contact. It's really important to know that we are talking about one point of contact. So for a circle, we could simply follow Euclid and say that a tangent is a line that intersects the circle once and only once, as in this figure below. So we can see that there is a point on the circle, and the tangent line is considered the line that goes straight through that point and not through the other points. So what kind of line would go through other points? Well, if you draw the line differently, say you draw the line, if you're watching my mouse, if you draw it this way, then you can see that it would cross 2 points on the circle. That would not be a tangent line. So it is the one that brushes the surface and goes through the single point. For complicated curves, this definition doesn't actually work because it is possible that tangent lines do go through 2 points, but mm, but the point that the tangent line is tangent to, the line needs to go through the point but brush the surface of the curve. So you see here is the point that is important. The blue line is not a tangent line because although it does go through the point in question, it does not brush the surface of the curve. It intersects, it cuts it. It's not a tangent line. So notice the red line is correct. Although it intersects the curve somewhere over here, that's not the general area that we're focused on. We're focused on this point. So this point, the tangent line goes through the point, and notice that with the black curve, the red line is brushing the surface of the curve. First example, let's find an equation of the tangent line to a curve, the parabola y equals x squared, at a very specific point on that parabola. So now this example, we're going to walk through the steps in the PowerPoint with the solution, and then I have a follow-up example which we'll do out together. So we will be able to find an equation of the tangent line as long as we know one other piece of critical information. So if you think about it, y equals mx plus b, that basic linear line that you learned back in algebra class, you need either 2 points on the line in order to find an equation, or you need a point and a slope in order to come up with an equation. But we don't have either of those. We have an equation to a curve that we're tangent to. That is not the equation of the tangent line. Now we have the point at which the tangent line intersects. So we have 1 point on the line, but we know nothing else about this line, except for the fact that it does brush the surface of this parabola at this point. So what the heck do we do? So the first thing we're going to want to do is we're going to want to take a look at our slope formula. So if you recall, the slope formula for linear lines is the y-coordinate minus the second point's y-coordinate divided by the x-coordinate of the first point, subtract the x-coordinate of the second point. Now, the second and the first points, it doesn't matter in the order in which you subtract as long as you're consistent with the numerator and the denominator. So here they're showing us that the y values, the outputs, are going to come from the equation, the parabola, and the x are the values that we're going to choose to input into to find y's. So we know that one of the points is a 1. So if we put 1 into our parabola equation, let's review our, oh, I skipped a slide. Our parabola equation is x squared. Um, let's probably talk about this slide that I missed. So our goal, this is where our goal is. This is the visual slide. So our goal is to find this red line. But we know that this red line only goes through one point that we know of, and we know nothing else about the line. We don't know the slope, we don't know another point. But what we do know is another point on the parabola. So we're going to use something called a secant line. Okay, so, ooh, sorry about that. A secant line is a line that's like an average. If you think about it, you are splitting the difference, so to speak. So if you create a line between 2 points on the parabola, that straight line, this blue line, is called a secant line. And that you could see that there's clearly a difference between the slope in the blue line and the red line, but also notice how far apart these points are. So the point that we're trying to get to is that if we take this second randomly arbitrary chosen point and we move it closer and closer and closer to the point in question, then the secant line will align closer and closer and closer to the tangent line we are trying to find. So right now we are using the estimation, the averages from the secant, those slopes, to get our best guess, our guesstimate of what would the slope be of the actual tangent line. So to do that, now we're at that slope formula. So to do that, we will want to, you see, this is the output of a second point. If I put 1 into the function x squared, I'm going to get an output of 1, hence the point being 1, 1. We knew the x and the y value of that point we are trying to draw the tangent line through. So we have the y value here, which happens to be the same number as the x value. Now we need another y value on the parabola, preferably super close to 1. And so like maybe 1.1 or 1.01 or 1.000001. The closer we get, the more accurate our estimation for the actual slope of the tangent line will be. So for instance, let's say we decided to put in the value 1.5. So that is half of a point away from our designated intersection point for the tangent line. So this 1.5, we put it into x squared. 1.5 squared comes out to be 2.25. So then we replace the x squared with the appropriate y value. We replace the x with the appropriate x value, and we calculate the slope of this secant line. So the slope of the secant line comes out to be 2.5. Now, when we just do this once, yeah, we could use 2.5 as the estimated slope for the tangent line. But we know based on just that simple picture, let me back up and show that picture again, that if this point is too far away, the slopes of the blue secant line and the red tangent line not the same, nor are they remotely close. So we want to make sure that we know what that slope is. So the best way to do this is to do this a couple times. The more that we get closer and closer to the point, we should be able to recognize a pattern. And then that pattern, which we're going to learn is called a limit, is going to tell us what is the slope we are approaching as we get closer and closer and closer with those secant lines to the tangent line. So we start building a chart. We say, okay, our goal point is 1. Notice that 1.001 is really close to 1, and so is 0.999. And the goal is to approach from both sides of the point. So you want to pick x values that are less than 1, and you want to pick x values that are greater than 1, so that you have secant lines and slopes that are approaching the point in which the tangent line is going through. So in doing that, over here we see we started with an x value of 2. If we put 2 into the parabola, the output is going to be 2 squared, which is 4. We calculate the slope formula, 4 minus 1 over 2 minus 1, and we get a slope of 3. Then we say, you know what, let me take that a step closer to the point I'm actually interested in, and let's put the input of 1.5. So you put 1.5 into the parabola, you get an output, and then you do the slope formula, and you get a slope of 2.5. And then you get even closer to 1.1. The slope comes out to 2.1. The slope, not the y value. 1.01, you do all those calculations and you get a slope. And notice the trend. Once we build this chart, I can see that 3 is quite different from what I'm approaching as the slope as a tangent line. And it seems to be approaching 2, but to be completely sure, you also want to check secant lines on the other side of the point. So for example, if we start at 0, which is less than 1, then if I put 0 into the parabola, the output is 0, and we have oh, I had to think about that one. So even though the y values so the y value to this is 0, and we have the 0.11. So we are going to do 0 minus 1 over 0 minus 1, and we get a slope of 1. Okay, so below the point, we have a secant line with a slope of 1. Now, again, we're going to gradually step our way closer and closer and closer to 1, throw those input values into the function x squared, get our y values, our output values, calculate the slope y2 minus y1 over x2 minus x1, and that's these numbers here. And we can see, although the slope one step away from the point is 1, as we gradually get closer and closer, we know that the slope is also approaching the value of 2. So it is a good guesstimate for us to guess that if we were to be able to calculate specifically exactly the slope of the tangent line, it would be 2. Okay, so using that information, we then say, all right, well, if we know our slope is 2 and that line is going through the point 1, 1, then we can use what's called a point slope form, which is y minus y1 is equal to m, the slope, times x minus x1. So notice this is the y1 and the x1 point, 1, 1, that we're interested in making a tangent line. We slap in the slope. You use your algebra to distribute the 2 throughout the parentheses, add this one on the other side to get your y equals mx plus b form of the line. So this tells us that this is our best guess for the tangent line based on the information we have. And it is very accurate because that's the exact equation for the tangent line. Here's the illustrations on what we were doing. We first took a point very far away from the point in question and created a secant line. Now, the slope of the blue line was very different from the red. But as we brought that point closer and closer to the point P, notice the difference, the gap difference between the blue and the red line. You see how the gap is getting smaller and smaller because we were approaching what the actual slope of the tangent line was going to be. And the same thing happened as we picked values that were much smaller than P. Okay, notice that this blue line really is not very helpful. It is very different. It has a completely different sign on the slope. But as we brought the point Q closer and closer to P, you could see that it was lining up closer and closer to the correct tangent line. Now let's try one together. So to do this, I am going to jump over to our whiteboard, share my whiteboard, and we are going to do this problem together. So the problem states that we have an equation y equals x squared minus 3 is our parabola, and we are curious about the point 1, negative 2. We want to draw a tangent line through this point 1, negative 2, but we need to build a table of values in order to do this. We need to know these slopes. So we need inputs. Now I'm going to make my chart 3 columns because I actually want to write my x's and y's down. We have our slope. And again, we want to pick values that are less than 1 and do a chart with values approaching 1. And we also want to do a chart of values where we pick the values greater than 1, but still we're coming backwards and we're trying to approach 1. So let's say I pick the x value of 0. Okay, so we put 0 into our function. 0 squared minus 3 is -3. Okay, so now we have the point 0, -3 that is on our parabola. Now we calculate the slope of that point to our focus point. And again, we do that by doing y2 -3 minus -2. So those are the y values over, make sure you stay consistent. Since -3 is paired with 0, we're going to put 0 minus 1. Okay, so we have -3 plus a +2, so that gives us a -1. And 0 minus 1 gives us a -1. Goes in my way. Here we go. And that gives us +1 as our slope. Let me move that one out of the way. Okay, so we have a slope of 1 for the secant line from x equals 0 to x equals 1. Now let's get a little bit closer to 1. So let's go to 0.5. Okay, so if we do 0.5 as our next point. Now, unfortunately, I do not have a virtual app for my calculator on my home computer, so I cannot use the calculator in front of you guys, but if you need help with your calculator, that is something we can do in our on-ground portion of this course. So if I am putting in my calculator 0.5 squared minus 3, I'm going to get the y value. My y value comes out to be -2.75. Now I'd want to calculate the slope. So I have -2.75 minus -2 divided by 0.5 minus 1. Okay, so if I calculate this out, comes out to a slope of 1.5. Okay, so that's a big jump from our first secant slope, which was 1. Let's get even closer to 1. Let's go to 0.9, 0.9 as our input. So we're going to put 0.9 squared minus 3 in our calculator to get an output of -2.19. And we calculate the slope again. Yes, this is a very repetitive process, but it gets the job done until we learn more. Eventually, throughout this course, we were going to learn how to do this much quicker using derivatives, but it's really important for us to understand where the derivatives came from and what the heck are they telling us. We just say use this derivative, you're using a word that you don't even understand. So it's really important to keep that in mind. These first couple sections we're covering, they are leading us to understanding what a derivative is. So -2.19, oh, there we go, minus -2 divided by 0.9 minus 1. So we're going to put that into our calculator. And we get a slope of 1.9. Okay? And we should probably get even closer, like 0.999. All right, let's do that. Let's do x 0.999. Can't fit it on the bottom, so we're going to do it over here. Okay, so 0.999. We put that in our calculator, we get an output of negative 2.002. And if you put through the slope formula like we've done for the last 3 examples, the slope comes out to be, hold that thought, for whatever reason I can't find it in here, so let me calculate it real quick. Negative 2.002 minus negative 2 divided by 0.999 minus 1. And we get a slope of 2. Oh, so we see the pattern here. We can see that we started at 1, and as we got closer and closer and closer to the x value of 1, our slope went from a 1 in the secant lines to a 2. Now, to verify that right now, I'm assuming the slope of the tangent line as I got really close to 1 was approaching 2. I want to do this from the other side. Let me erase this out of the way. Just need to verify that the slope is indeed 2 by coming from the other direction. So right now we have come from the numbers less than 1, the x value is less than 1. But now let's try to come from the other side. So again, our equation, our point, let's come from numbers bigger than 1 this time. So let's start very far away. Let's start at an x value of 2. Again, we put 2 into the equation, so 2 squared is 4, minus 3 gives us an output of 1. Now let's put it into the slope formula. So we have a y value of 1 minus a negative 2 divided by our x value of 2 minus the x value of 1, which gives us a slope of 3. Okay, I'm not writing the workout anymore. I'm doing it in my calculator, but I am walking you through. I'm talking you through what I'm typing in my calculator. And you've seen a couple examples already. Let's get closer. Let's do 1.5. Okay, so we do 1.5 squared minus 3. That gives us an output of 2/3. Oh, no, I typed it in my calculator wrong. I knew that was weird. This is better. Negative 0.75. That makes a heck of a lot more sense. Now we're going to do negative 0.75 minus a negative 2 divided by the x values of 1.5 minus 1. And we get a slope of 2.5. So we're seeing the pattern. We're seeing the slopes of the secant lines approaching the same number, seemingly, as the other side. It seems to be coming down to 2. But let's be sure. Let's just jump right to 1 point. You know what? Let's not jump that far. Let's do 1.1. Okay, so we have 1.1 squared minus 3 to find our y value. Our y value is negative 1.79. Let's take that y value, subtract a negative 2, divided by the subtraction of the x values, 1.1 minus 1, and we get a slope of 2.1. Oh yeah, definitely looks like we're getting closer and closer to 2. Let's do one more, super close to 1 from this side, 1.001. Let's see what the y value on the parabola is for 1.001. Square it, subtract 3. We get negative 1.99799, blah, 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 blah. It keeps going. Put it into the slope formula. That y value, negative 1.99799, blah, 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 minus negative 2 divided by the subtraction of the x values, 1.001 minus 1. And we get a slope of 2.001. So now I am much more confident to conclude that the estimated tangent line slope at the point 1, -2 to the curve x squared minus 3 is indeed 2. So now I am feeling pretty good about this curve at this point, that the slope of the tangent line, oh, my stylus is failing me here. Here we go. M tan. So M is the universal letter for slope, and we're just going to do a subscript of tan to represent that this is the slope of the tangent line, is the value of 2. Now we're going to use the point slope form. So y minus y1 is equal to m times x minus x1. That is the point slope form of a line. In general, I like using the version m times x minus x1 plus y1, since we have to solve for y anyway to get a useful slope-intercept form of a line. So let's plug in our numbers. So we have y is equal to our estimated slope of 2, x minus the x value, which is 1, plus the y value. Notice that the y value is a negative, so we're plus a negative 2. Distribute, simplify, so we have 2x minus 2 minus 2, which gives us the equation of our tangent line. Y equals 2x minus 4. All right, let's head back to the PowerPoint. The velocity problem. Let's talk about our velocity problem. So suppose that a ball is dropped from the upper observation deck of a tower in Toronto. Okay, this tower is 450 meters above ground. Find the velocity of the ball after 5 seconds. Okay, let's walk through this example together and how we would go about making this happen. So, through experiments carried out 4 centuries ago, Galileo discovered that the distance fallen by any freely falling body is proportional to the square of the time it has been falling for. This model for free fall neglects air resistance, so keep that in mind. So if the distance fallen after t seconds is denoted by s of t, function notation, and measured in meters, then Galileo's law is expressed by the following equation. We would say that the distance of the ball that has fallen for t seconds can be found by 4.9 t squared. Now, where that 4.9 comes from has to do with gravity and gravity's speed. But we won't get into that right now. We'll be using gravity a lot in this course, but I'm sure you have also used it a lot in a physics course if you have taken physics as well. And you've probably derived this. The difficulty in finding the velocity after 5 seconds is that we are dealing with a single instance of time. What is happening at exactly 5 seconds? So if you think about it, when a ball is dropped, the ball is starting at 0. We're just dropping it. We're not pushing it. We don't give it initial force. We're just dropping the ball. So it starts at 0. But as gravity is pulling this ball down to the ground, it's going to pick up speed. It's going to increase velocity. So after I drop it 5 seconds later, it's not going 0 meters per second anymore. It has a speed, right? So that's what we're trying to find out, but we're trying to find out what is the exact speed at 5 seconds. However, even though we can't find the exact speed, because we don't know enough quite yet, we can approximate the desired quantity by computing the average velocity, secant lines, over a brief time interval, getting closer and closer to our desired time 5. So we are doing the exact same process we just did with finding the equation of the tangent line, but now we're doing it in a context of a problem. So the average velocity, slope, change in position, y2 minus y1, over the elapsed time, x2 minus x1. This is the interpretation of that basic generic algebra formula that you probably just really didn't know what the applications were for. So if we say, all right, let's pick a time close to 5, like 5.1 seconds, we find the velocity at 5.1 seconds, subtract the velocity at 5. Sorry, not the velocity, the output, the distance. Do this again. The distance after 5.1 seconds minus the distance after 5 seconds divided by the time that has elapsed. So we went from 0 to zero point 0.1 second was the time interval. We put it into Galileo's formula. So 5.1 is the input. We square it. We multiply it by 4.9. 5 as the input. And where we got this 0.1 was that we subtracted 5.1 minus 5. That's how we knew the time that elapsed. 0.1 of a second is what elapsed from 5 to 5.1. And it comes out to be 49.49 meters per second is our best guess for how fast this ball is going at exactly 5 seconds. Now, this is an average velocity using a secant line, but we used an average that was very close to 5. If we wanted to get more accurate, we should use numbers even closer to 5. So if you're looking at the time interval between 5 and 6, the velocity of the ball, average velocity, is 53.9. And we just calculated the time interval between 5 and 5.1. The ball was going 49.49 meters per second. We close it in even more. We get 49.245. Get even closer and closer. And again, just like we did with the tangent line problem, I can see that we are approaching 49 meters per second for the exact velocity of the ball at exactly 5 seconds. So this concludes our lecture on tangent lines and velocity problems. And I will see you all in class to work on some of these problems together next week, or this week rather, when you see this.